Hello everyone, my name is Christoph and I'm here to do a presentation on the electric force and field. There's a couple of goals I want people to get out of this video who watch it. Basically, by the end of this video, you should be able to tell if there's one charge in a given area. You should be able to tell where the electric field is pointing, and if there's two charges in proximity of each other, you should be able to tell where the respective electric forces of each of the charges are pointing. Yeah, so that's the mission goal, I guess you could say, for this video, and let's begin. So the way this video is formatted is I have different slides with information with regard to the electric force and field, magnitude, direction, and so on. Each will basically outline a different step. So to begin, we have the electric force. Now, basically, the most important part for you to get out is on the right side of this slide. So everyone knows like how magnets work, right? If you have a negative and negative, they're not going to like each other. Positive, positive, they're not going to like each other. That's shown by these bottom two circumstances. But if you have ones with opposite charges, positive and negative, they will attract to each other, which is what this is shown on top. Basically, if you think about it like that, you can determine where the electric force is facing. When I say the electric force, it's basically like where the charge wants to go. And so what we have here is we have bigger charges impacting the smaller charges. You can tell that they're smaller because of the size of the charge I drew them as. The size represents the magnitude. It's not really relevant here, but we'll keep going. So in this situation, the electric force of the different charges, they basically say where they want to go. Like I said, opposite charges, they want to go together. The same charges, they want to go apart. Yes, and so on the left side, we have Coulomb's law. This is basically if you wanted to find the magnitude of the electric force, given that you have a source, a charge, and a radius, so like a distance between them. Okay, so moving on, we have the electric field. Now, there's a couple things here that is really important. First of all, we'll begin with the left side this time, so the equation. So you have the electrical field, which is E, is equal to the electrical force divided by the Q, or the charge. So some very important things to know is that the electric field is a vector. So as basically this pertains to electrical field is the farther you go away from the electrical field, like basically the weaker it is. Also, it has direction is important because it's a vector, which will play into another slide coming up. So things to keep in mind with the electric field is that positive charges, the electric field points radially outward. So as shown by this diagram up here, as you can see, E is pointing outward. So it's basically, if you want to get, I guess it's going away from the charge, right? So it would just keep going here. It just keeps going outward, right, forever. And then basically it's the opposite for a negative charge. E points radially inward, so it would point towards the charge itself. And that does play a role with the electric force, and that's coming up. And that's coming up with direction. So direction is kind of important. You basically, the same equation as the last slide is even more vital on the slide here. Let's just get into it. So changing the sign of the charge changes the direction of the electric field. What do I mean by that? Well, we don't even have to look at the diagrams. We can just look at the equation, right? So in the equation, like I said earlier, the electric field is equal to the electric force divided by the Q of the charge. That's shown by this over here. Same as the last slide, right? So let's say we had don't even look at the right side. Yeah, let's say we had a positive charge, right? So if we had a positive charge, that means in the field is never going to be negative. That means you'll have positive over positive, which means it's a positive value, which means that the electric field will also be positive and the charge will be positive, which means that with a positive charge, as noted down here, positive charges will experience a force in the same direction as the electric field. Now, if we were to plug a negative into the Q, the negative charges experience a force in the opposite direction as the electric field. So what do I mean by that? So if we look at these diagrams over here, we have a larger charge with an electric field with respect to the charge. So like what confused me at first, and might confuse you as well, is that you're like, why don't these both have electric fields? Well, they do, but we're only really talking about the larger one creating the electric field, and we're trying to find the force of the smaller charge being created because of the electric field of the larger charge. So what do I mean by that? So if we look at the top situation, we have a positive charge with an electric field pointing outwards. As I said on the last slide, it points radially outward from the charge, right? So now if you go down to the the bottom rule, you'll see that negative charges experience a force in the opposite direction as the electric field. So because the electric field's pointing outwards, we know that the electric force will point inwards, and that will make them connect to each other or want to be attracted towards each other. Now, in situations where they're not attracted to each other, we have on below. So if we have a large positive charge that's giving out a electric field onto this other charge, we know from the second rule that the positive charge will experience a force in the same direction as the electric field. And another way you can verify that, if you don't really understand how that works, it's just like, okay, I have a positive magnet in another positive magnet. They're not going to want to go towards each other because of the electric force. That's another way to think about it. But the reason that does that is because the electric force is in the same direction as the electric field, as shown by the second example. Now, the bottom example, we have a negative charge giving out a inward electric field towards the charge, and we also have a smaller electric charge being impacted by that. The electric force of the charge is opposite to the electric field that's impacting it. That's shown from this bottom point right here. They will repel each other, and they don't want to go towards each other because of the electric field. It's opposite of each other. So basically, if you knew the electric field, you'd be able to find the electric force of the object. Also, if you were to find the electric force, you would know the electric field in turn, based on how the charges are acting and the original charge that's giving off the electric field. Moving on, we have magnitude. So often in problems, they will ask you maybe the direction of something, but they want to know maybe a specific value of the electrical field or the electrical force that's being created from one charge, two charges, 2+ charges, doesn't matter. Different situations get more complicated, and I'll discuss those on the next slide. But these are different equations that you'll need for finding those respective values. When describing these equations, I'll first note that k is a constant, and it's 9 times 10 to the 9th. And that's just what it is. I don't remember the specific name, but that's just what it is. Q source is basically the charge that's impacting a smaller charge. As I had on the previous slides, I had basically a very large charge impacting a smaller charge. And then Q of charge would be the charge of the smaller one. That's what that means. R is the distance from the center of the charge creating the field to the point in space that you want to determine the electric field. So it could be anywhere between two charges, basically. And that's for finding the electric field down here. So if I wanted to find the electric field, I would use this equation, right? I could either use the source and charge one, or I could just you'll end up. So if I wanted to find the electric field, I would you could use the Coulomb's law, or you could also just use this one, because you don't even need the second charge. Oftentimes it'll ask you a random point in space, and the second Q charge is irrelevant and it's not vital to the problem. Now, a common misconception that happens is some students will find a negative E value because they plug in a negative charge or a negative Q. Because K is constant and it's positive, R is a distance, is positive, they'll think that, okay, I'm going to plug a Q in for my charge and it will be negative. That's wrong. You don't do that. Now, see, if you were to, logically that makes sense. You're like, okay, negative charge, it's going to be a negative Q, right? But for your Q, you always want to plug in a positive value, even if it's negative 4, even if the charge says negative 4, you want to plug in a 4. The reason for this is that it doesn't really tell us a valid direction of where the charge is. If we have a charge, we already know that the electric field is going to point radially inward towards the charge, as shown by this diagram right here. But the problem with the negative is it doesn't really tell us the exact direction of it. If we had a point over here, we would know that the force points inwards, right? We would know the points points inwards, but it could point left. It could point right, downwards, upwards. It doesn't tell us an exact direction, and it kind of confuses us. So what we do basically is we keep the charge positive, and we basically state the direction ourselves. So you could use degrees, or you could say southwest, east, north if it's on a direct, if it's on pi, 1/2 pi, 3/2 pi, or 2/2 pi radians. That's what you would do. Important to keep E positive and state the direction afterwards of the electric field. So moving on, I'm going to talk about the application of if a question were to ask you to find the electric field of a charge. So what do I mean by that? So we have 3 different circumstances that are the most common. You have a single charge, 2 or more charges, and it's in a 1D model, and 2 or more charges in a 2D model. So the simplest one is a 1 charge. system. Basically, you have one charge in the center, and you are asked to find the electric field at a point away from the charge. Basically, all you do is you plug in what you have. You plug in K, you plug in Q, make sure your Q is positive, even if the charge is negative, and you plug in the radius from that point to your charge. It's not that complicated. Next, the 2 or more charges in the 1D model. This gets a little bit more complicated because basically 1D model means it's like on a timeline, you can think of it as. And what you do is you find the electric field of each using the equation above. And what you do is after you find each respective field, you add them together if they're in the same direction. You add them together if the electric field is in the same direction, and you subtract them if the electric field is in the opposite direction. Moving on, lastly, for the 2 or more charges, 2D, you have introduction of the y dimension. So that's what the 2D means. So not only do you have charges on the timeline, but you also have them in the y dimension. So you could basically have a point where like maybe your charges are on -3, 0, and 3, 0, but you have it's asking you to find the electric field at point 0, 3. That's when you're gonna like run into like what is going on, because it adds a whole nother dimension to it. So the first step you need to do is you need to find the radius of to the point, and the way you do this is you use Pythagorean theorem. I gave you nice numbers, so it's not that hard. You just do 3 squared 3 plus 3 squared plus 3 squared equals c squared, and you add that together, find the square root of each side, so you get your answer, right? Next thing you want to do is you want to focus on finding the components of each electric field in each direction separately. Sorry, it's misspelled on the slide here. So what do I mean by that? So you want to find each respective y and x value for the electric field, and you do that by using this equation up here for the y and x value. And so you might ask, like, does it what changes when y and x? And what changes is that you have to use cosine to find the x values of your sign, because obviously there's a degree, and the y value adds a degree component that changes the actual value. Like the value is not what it would be; it's a little bit less because of the sine and cosine. Sorry, because of the cosine. And then for the vertical value, you want to use sine. After that, you basically, again, you add them together, and if you get nice numbers, a lot of things actually seem to cancel out, and then giving you your number. So that's actually the last slide today. I hope that you were able to understand me a little bit with regard to the electric field and electric force. It's kind of a complicated subject. I recommend watching this video again, and I will shout out Khan Academy. Definitely helped me understand this to a very large degree. Even if you can tell that I understood this, I do. And I would definitely recommend checking them out. I'll try to post some more guys like this in the future. Thanks for watching, and signing out.